Okay, good morning. Let's start our lecture today. So before we start, I would like to recommend this book for Aeroelasticity. In the last lecture last week, I added a short beginning in the office, recommending some books, but this one is really the one I'm following. I think is a very easy to follow book, very comprehensive, covers static aeroelasticity and also flutter. So I'm going to write here again, the name of the book is Introduction to Structural Dynamics and Aeroelasticity. Okay, so the authors are Dewey H. Hodges and G. Alvin Pierce. Right? So you can find this book in the library. It's a thin book, but it has many proposed examples, which I'm going to propose to you to do at home as well. So, but it's the book I follow. I strongly recommend you to get this book for aeroelasticity, right? Okay, so let's just do, before we start with the static aeroelasticity today, let's just recap a little bit what we did last week for vibrating beam. So we arrived at this differential equation on the deflection of the beam. EI, so I'm just writing what we derived last week. Now a second derivative in order to time. Equal to 0 because we were considering free vibrations, not forced vibrations. So we are looking for the natural frequencies, right, of the beam. So one thing I would like to emphasize here, and I forgot to say last week, is this dA that you see here. This dA is the cross-sectional area of your beam, right? So we are considering in this analysis the cross-sectional area to be constant for the beam, right? Not changing. That will introduce more complexity. So take this dA as the cross-sectional area of your beam, all right? And then we can say that this rho dA, we can say, is basically the mass over a unit length, right? Or if you want, if you multiply rho dA by a length, you will get a mass, right? Okay? So that this is the first point I would like to address with you, which was not clear from last week. Also, from last week we derived the weighted residuals, a numerical technique which you use a lot in FEA, and we did that for a beam deflection problem. Remember, we built a residual. So what we did was we built a residual. Then we multiply that residual by a weight function. Okay? And then we said, in the entire domain, we did an integral in the domain, so we added these weighted residuals all over the domain of our beam. And we imposed then that this weighted residual equal to 0. Then we solved this equation for the unknowns which were obtained from our approximation function. So basically we said that instead of having an exact solution V, we had an approximate solution in this form, which is a summation of the product of shape functions times, so these shape functions will depend on the coordinate x of your beam, times unknown coefficients ai. So when you replace this approximation function in your differential equation here, you will get a residual, which you then integrate, and then your unknowns are going to be these coefficients ay, because these shape functions, as we are going to see now, they are known or given, all right? So let's see how can we do this for this differential equation that we have using the weighted residuals. So we did last week for the static beam deflection. We are going to do today for the dynamics or the vibrating beam, okay? Right? So we will build an approximation in the form, so for the deflection, V, this is going to be my approximation. So don't forget our V depends on the longitudinal coordinate of the beam, x coordinate, and also depends on the time, because this is a dynamic problem. We are going to build an approximation in this form, a summation again from I equal to 1 up to n. N is the number of terms you are going to have in this summation. And we are going to decouple again into a function that depends only on time and a function that depends only on the spatial coordinate x of the beam, all right? Like we did last week, remember we did the analytical solution last week for a pinned beam. We used the method of separation of variables, right? Remember that? We separate into this C, which is only a function of time, and a function phi that is only a function of x. This phi is our shape functions, right? For this function phi I, we can use the same functions we used before, combination of sines and cosines. We did this last week, remember? If not, it's in your video lecture in Panopto. So we can use this function. And for the function phi, we are going to see which function we are going to use later. But just an example for this function that depends on time, we can use exactly the same function we used before last week. And if you do the second derivative, like we did last week, we concluded that this second derivative is minus w squared, with the natural frequencies squared, times the function xit, right? The difference here is now from what we did last year is we are going to have not only one function phi, function of time, but we are going to have n functions phi as a function of time, right? So the more functions phi we have, or the higher this n is, more accurate our solution will be. Don't forget, this is an approximation method. Something you do in FEA, right? This is equivalent in FEA as you refining the mesh, getting more nodes, getting more n terms in this summation, right? So we are going to have many functions phi, but we concluded last week that the second derivative is equal to minus w squared times phi. All right? So if you do the second derivative of this function, you get that conclusion. All right? So once we have the approximation function, what we have to do is we have to build our residual. Okay? So we have to build our residual, Rn. This subscript n means depends on the number of terms I consider in this integral. Okay? And what I'm going to do in order to get my residual is I'm going to replace my approximation function, this v hat, into this my differential equation, right? And then I will get the residual because this v hat is not the exact solution, is an approximation. So if I replace this approximation into my differential equation, I will not get the second and right equal to 0 of that equation, but I will get a residual. Yeah, makes sense? I think that the name of the method says everything. So if you replace, you will get what? Well, the first one is you have to do 4 derivatives in order to x. So once you have these two functions here, function phi depends only on the time. So the derivative in order to x is going to be only the derivative of this shape function phi I. Yeah? So we can write something like this. I'm going to have summation from I equal to 1 to n phi I t times the fourth derivative 1, 2, 3, 4 of phi I in order to x. Yeah? So I did this term here in of my differential equation. So one more thing, I am in fact doing something more. I am multiplying both the left and right hand side by EI. So if I do that, I will have EI here, and EI will disappear from the denominator here, right? You agree with me? So in that case, of course, I need to include here times EI. And then, yes, I can say, when I replace in this fourth derivative my exact solution V with my approximation, I get this term here, right? Now I need to do this bit here. So this bit, I have the second derivative of my approximation function in order to time now. So I will need to derive only my phi I function, right? So I will have plus rho dA, or if you want, we can put everything inside the summation, is fine. Rho dA times the second derivative of my function xi times the shape function phi. And this is my residual. Okay? Now, once I have my residual, which is this one, I'm going now to use the Galerkin method of the weighted residuals. So I can write here, using the weighted residuals with the Galerkin method. What I have to do is integral from 0 to L, which is the domain of my beam, goes from 0 to L is the length of my beam, of a weighting function, Wi, which in the Galerkin method, the weighting function is equal to the shape function, which is phi. I'm going to use a different index now, j of x. So this is my shaping function, which in Galerkin's method is equal to the weighting function. And I need to multiply now this weighting function by the entire residual, which we derived here already, okay? So this is my copy, paste, maybe make it a little bit smaller like this. Yeah, and this needs to be, of course, integrated in the x direction and needs to be equal to 0. Yeah? Okay, are you seeing what I'm doing? Any questions so far? So we have our differential equation that we derived last week. That one is in the top. You don't need to copy all of this for two reasons. I'm going to upload the videos, as I always do. And I derived everything by hand. I have a PDF file of all of this. I will upload in Blackboard. I know I said that last week, but the reason why I didn't upload last week was because it was not completed, the notes. Yeah? But now they are completed. I will upload, all right? Just after this lecture. Not really after, because after this I have a social gathering with year 1, which I hope there's free food there, because I go straight away from here to there, so no time for lunch. But anyway, but after that meeting, I will upload the video lecture and these notes in Blackboard, okay? So you have everything, don't worry. It's better just to pay attention, and if you are not following, stop me, okay? Right? Okay, so this weighted residual, so don't forget, we are going to have n shape functions, or n terms in this summation. This comes from this approximation that we built, right? We're going to have n. More n means more accurate. And this means that if you look carefully at these two terms, this one here in red and this one here in green, once you do these two terms, you will get something like this. The first one will give you the stiffness matrix, K, which in FEA you are quite familiar, right? And this stiffness matrix is going to multiply my functions phi t, where, don't forget, I can put here this I goes from 1 to n, is the number of terms in my approximation. This one here in green, I said before, is going to be my mass matrix, M, which are going to multiply, look at this, this is the acceleration, right? The second derivative in order to time. So this mass matrix is going to multiply double dot I t. And this is going to be equal to 0. So I will have a system of equations like this, which you are more familiar, right? You are familiar with this. This is the equations of motion. Basically, you will have, there's one term here that is not appearing, which is damping. We are not considering damping here, right? But these equations of motion, if I replace now, maybe I copy to a new slide all of this. If I replace now in these equations this term, the second derivative of my function xi, which is minus wi squared times my function xi t, yeah? I will have a system. If I replace, I will have a system which is going to be stiffness matrix, K. Why is it doing this? Stiffness matrix, K times xi t is going to be equal to wi squared. So I send to the right hand side, I change the signal, CIT. Sorry, I forgot to include the mass matrix times mass matrix times CIT as well. Right? And if you look carefully, this term cancels with this, so at the end you will have an eigenvalue problem. Right? At the end, I can write here, this is going to be an eigenvalue problem where you can solve for Wi. Okay? Right, so the problem now is how do we build these stiffness and mass matrices. So they are, so the stiffness matrix, so let's do that example for, but before that, let me go back to our weighted residual here, so let me copy. There's one thing that we usually do in FEA, which is integration by parts. The reason is, in this weighted residual here, we have this fourth derivative. Okay? So when we integrate by parts, we reduce this fourth derivative into a second derivative, all right? And of course, and we need to apply the boundary conditions. You know the rule integration by parts, right? You can always reduce higher derivative into a lower derivative, integrating by parts. So that's what I'm going to do now. I'm going to integrate by parts. And then if you do that, you will get something like this. And if you change the summation with the integral, if you swap these two, which you can do, you will get some summation I equal to from 1 to n. I can open this big one. You will get the function xi, and then once you integrate by parts, you will get this j second derivative and phi I second derivative as well after integrating by parts. Okay? And you will get then here your second derivative, so that I was missing there. And of course there's one more thing missing here, which is the integral. And this integral here is in the x direction. That is correct. And you will have here as well the integral. And you will have now rho dA multiplying phi j x and phi I x. All right, so the only thing I did in this step was just integration by parts, mathematical manipulation, nothing more than that. And now I'm going to say that my stiffness matrix, my K matrix, is going to be given by the integral from 0 to L of EI times the second derivative of my shape functions okay, while my mass matrix is going to be given by integral from 0 to L rho dA times my shape functions. J I. So this is a matrix, of course. But if you don't want to do this way, you can say this stiffness matrix ij component. Each ij component in your matrix, don't forget this I and j varies from 1 to n, depends on, I can do the same for the mass matrix here, it depends on the shape functions I and j and the second derivative of the shape functions, right? So this, I think it makes a lot of sense. Look at this. For the stiffness matrix, this EI is the flexural stiffness of the beam, right? So it needs to be included in the stiffness part. And for the mass matrix, this rho dA is the mass per unit length, which is a term that should be included in the mass matrix. Make sense or not? So the only thing we have to do now to solve this problem numerically, and I'm going to show you the results, is to define these shape functions phi. Right? If we define these shape functions phi, then we just need to integrate them, get the stiffness matrix, the mass matrix, and solve an eigenvalue problem for the natural frequencies. That is quite easy to do in MATLAB, for example, right? Once you get this stiffness in mass matrix, you put them in MATLAB. You ask MATLAB to get ij function. MATLAB automatically will calculate for you the natural frequencies. Okay? All right, so let me copy these two guys here. Oops. In a different slide. Maybe move this guy now to here, right? Make it smaller. Make it smaller. Maybe get rid of this guy. Sorry, I'm just rearranging this, otherwise I'm moving slides every time. Okay. Right. So for the shape functions, so we are going to start defining. So the strategy is you can use for these shape functions phi, you can use the same functions we used last week, those ones involving sines and hyperbolic sines, remember, cosines and hyperbolic cosines. But I'm going to do it in a different way. I'm going to use polynomial functions, but I'm going to start defining not functions phi, but the second derivatives. The second derivative, don't forget, is related with the moment, right, in the beam. Remember, the moment is equal to EI, second derivative of deflection in order to x. So this second derivative is related with our phi, second derivative of the shape functions, right? So the polynomial functions here that we choose, or the shape functions that we choose, there are some rules for these shape functions. They need to obey the boundary conditions, always, okay? They need to be linearly independent. They need to be a complete polynomial. This kind of thing. So I'm not going to deep into that because I just want to give you some, and you are going to study that further in FEA as well. But what I want to tell you now is that this second derivative function is going to be selected that respect the moment boundary condition. So we are going to do the analysis for a clamped beam now. Remember last week we did for a pinned. We are going to do now for a clamped beam. Okay? And I'm going to select this shape functions here. 1 over L squared. This L is the length of the beam. Then I have here 1 minus XL square. And then I have here X over L with an exponent I minus 1. If you look at this, okay, if you have a clamped beam like this, where this is my L, okay, if my x-axis starts at this point here, right, at this point, so if I replace in this equation x with L, I will get the second derivative equal to 0, which is correct because at the tip of my beam, the bending moment should be 0, right? On the contrary, you might say, okay, but at this point here, where it is clamped, the bending moment should not be 0. And it is not with these shape functions. Look at this. For the first shape function, when I is equal to 1, you get here 1 minus 1 is 0. So this term here goes to 0. It goes to 1. Any number with a power of 0 is equal to 1. And then I will get, basically, my second derivative is going to be equal to 1 over L squared. Okay? So it's not 0, which should not be. So you can see this polynomial function here that we selected, is based on the boundary conditions. They need to respect the boundary conditions. So we have the problem solved for the second derivative. This is our functions we are going to use. What about the shape functions phi? So we have the second derivative. What about shape functions? Well, shape functions, what you have to do is, if you integrate one time, you get the first derivative is going to be equal to the integral of 1 over L to 1 minus x over L squared. So when you integrate, you will have a constant of integration. It's similar like you did in beam deflection, right? And then you integrate one more time. You will get your shape function by integrating again. Don't forget, this is from 0 to L, right? From 0 to L. By integrating now the first derivative. And then you will get C1x plus a second constant of integration. The question now is, where do you get this C1 and C2? Well, you get again from boundary conditions. One boundary condition is the slope. The slope of the beam the slope is the first derivative, right? For x equal to 0, the slope needs to be equal to 0. No rotation. The beam is clamped. So if you replace in this equation, after doing this integral, if you replace the x by 0, you should be able to calculate C1, right? The second boundary condition is the shape function for x equal to 0 also needs to be equal to 0. It is clamped at that point, so the deflection there should be 0. And then, if you replace in this equation all the x by 0, you should be able to get C2. All right? So this is how we can get these shape functions. If you do all of that, you get a shape function phi I x, which is equal to, so I'm just going to write here so you have everything in the video. You don't need to go to the notes. But this is a very time-consuming and boring, tedious process to do those integrals. This is not what we are trying to assess here, so if you want, you can do it at home. You should get something like this. Is also in the Dewey Hodges book. So this is your shape functions, right? And then if you replace these shape functions in your stiffness and mass matrix, if you replace the shape function and the second derivatives, you should be able to get something even more horrendous, which is for the stiffness matrix, you get this 24 EI L power 3 just going to copy. A good way to study is you try to do this at home if you want, or do different examples for the beam. For example, what you can do is you can use these weighted residuals for the pinned beam we did last week. We got the analytical solution. You can try to get the numerical solution or using the weighted residuals in this way and compare the results. All right? And for the mass matrix, you will get something like this: the mass of the beam times the length times two constants P1 and P2. This P1 and P2 is a long constant. Okay, I can try to put them here. So P1 is equal to this. You might be thinking, are you going to ask this in the exam? Are you thinking on that? I can, not to get all the result, but at least to get the derivation of the equations of motion, right? Using the weighted residuals. I can ask that. But not asking all these final result solutions, right? Because you don't have time to do in the exam, right? But the derivation of the method, yes, you can be asked that. This is, I think is okay because you are also learning a little bit for FEA. So I just want to close this vibrating beam and start today the static elasticity, all right? Okay, so this is P1, P2 is a bit shorter. Normally, this is the best way to do this is in MATLAB. Okay, you put the shape functions and second derivatives, and then you ask MATLAB to build the stiffness and mass matrices. It's much easier that way. So this is the end calculations way, if you want, which is very time consuming. That's why we have the computers to help us solve this much quicker. But for the purpose of the lecture, which is to show you how accurate the method is, I'm just writing all of this so you can, that's it. You can then solve this at home and try to understand better the method. So if you do this and if you get the eigenvalues, you are going, so I took this figure from the Dewey and Hodges book. What you have here is, on this last row, the exact solution for the clamped beam, right? The first column is the number of terms in your approximation function, or the number of shape functions, or the number of elements in your mesh, in your FEA mesh. Yeah? So the more elements means, or the more terms means, more accurate your solution should be. So you can see for mode number 1, for W1, the first natural frequency, if you use only one term, you get 3.53. Two terms, you start to getting closer to the final solution. But after three terms, you converge completely to the final solution of 3.51602. Yeah? For mode 2 is similar. You can see the more terms you use, you are getting practically the same value as the exact solution. For mode 3, if you use only one or two terms, they didn't even put any value there. You are very far away. But once you go to three terms in your approximation, you get 66. The right solution is 61.69. But once you start refining, adding more terms, you're starting to get closer to the... So it's pretty accurate method, right? So you can... These are the... So what you have here is your natural frequencies, right? Mode 1 means W1, mode 2 means W2, mode 3, W3. Yeah? This n, don't forget, in your approximation function, you add summation of I equal to 1 to n of these functions. So the n is the number of terms you have, or the number of shape functions you have in this approximation. More shape functions, more accurate. All right? So this is for the clamped beam. So if you want to study this at home, do the pinned beam. The boundary conditions are different. And try, the exact solution I gave you last week. Try to do it yourself by hand. It's a very good way to study. But now I think we need to move on to static aeroelasticity. The first... So I'm just going to introduce you what we are going to do before we do a break. Right? So we are going to start now a very, very important topic, which is static aeroelasticity. Okay? If we don't have time to finish, we are going also to talk about... So we are going to talk here about divergence and aileron reversal. Oops. Aileron reversal, all right? We're going to see what this is and how critical this can be for aircraft. If we don't have time to finish, we need to continue next week. But anyway, next week we will start the dynamic aeroelasticity, or flutter, right? Don't worry if we take the 12 weeks to do all of this, because we are going to do revisions in week 31, 32. So we have time to revise everything that comes for your exam, right? In April or something like that, we will do 2 or 3 hours or more if necessary, right? So don't worry that we are going to do revisions. But I need to finish this in these 12 weeks. So we are in week 9. I think we are okay. Right, so what we are going to do is the analysis. So we are going to take aileron. Okay? So these analyses, they are conducted in the wind tunnels. So we have many... for example, in your wind tunnel, you have the working section. So this is the top view of your working section. What you do is you put your scaled model of your wing here, and you need to attach or clamp the beam to the walls of your wind tunnel. And then, of course, the flow comes in this way, right? The free stream velocity. The wing might have some angle of attack, right? And so what we are going to see now here is the cross-section of that wing in the wind tunnel. So one more thing I can say here, you can have different arrangements for the wind tunnels you want to do. You can have this one, or you can have now the side view. You can have the airfoil, and you can have a beam here that is clamped. So the airfoil is attached, the trailing edge is attached to the tip of the beam. So this is the side view, this one at the bottom. Of course, the flow goes this way, right? You can have different configurations. You can have also, for example, the side view, again, if you have your airfoil, you can have it connected by springs in these two terms in your wind tunnel. So you can have different configurations. So why am I talking about the wind tunnel? Because when you are designing an aircraft, you need to get the speed of your aircraft, after which you get divergence. Divergence means infinite lift on your wing, which you don't want that for sure, right? So when you are designing, so we go into, I'm going to show you, we put this in the wind tunnel, and we can predict experimentally as well. So we are going to predict analytically by a mathematical model this divergence velocity, but you can also predict experimentally in the wind tunnel. We are going to see why. So there are many different configurations for the wind tunnel. We are going to do our derivation based on this one. And so I'm going to say, so looking now at the cross-section or side view, I'm going to say that this airfoil is pivoted, and I will consider having here torsional stiffness K. This torsional stiffness, if you look at here, is the torsional stiffness of these rods, or if you want, in a real wing, is the torsional stiffness of your wing, right? So we are going to build a simplified model because, first of all, we are trying to understand the phenomenon. Yeah? That is one thing. So there are going to be 2 points in this airfoil that you know. One is the center of gravity, where we have the weight, W, yeah? The other one is the aerodynamic center, where we have the lift, and where we have the pitching moment, right? So let's call this one MAC, moment at the aerodynamic center, all right? So this is the stuff we are going to have. We are going to assume that, let's see if I can draw it properly. Not so bad. We are going to assume that this airfoil is with some angle of attack, yeah, alpha. So our free stream velocity is this vector here, u, yeah, so is facing the airfoil with this angle of attack alpha. What else do we need to have? Well, okay, let's say this pivot point, let's call it P. And of course, we need to have some dimensions here, right? So I'm going to try to draw the dimensions in green. All right, the first dimension we will need, let me just, this lift is too high. So let me put, oops, the lift here. So the dimensions are going to be, we are going to need this one. So from the leading edge to the aerodynamic center, I'm going to call this my AC, aerodynamic center. We're going to measure everything from the leading edge of the airfoil, right? The other dimension I need is the location of the pivot point, which I will call this XP, pre from pivot. I also need the location of the center of gravity. So this is going to be my location of my center of gravity, XCG, center of gravity. Try to give some suggestive names. And of course, I'm assuming this airfoil to have a total chord length, C. C is the chord length. So this is going to be the airfoil we are going to work and derive these important things, divergence and aileron reversal, all right? And I propose to do that after a break. What do you think? You want a break now or to continue? For me? Break? Yeah. So let me just put this smaller. Let's do then a break, okay? 7 maximum, okay? 7 minutes maximum. Are you ready to continue? So, by the way, thank you very much for your input last week in the things I like, things to improve. I looked especially things to improve, and one of the things was the break. Too short, so I gave you 7 minutes now instead of 5, so I hope. But anyway, your view is open and is going to be closed on, I don't know when? 24, which is next week. Yeah, so please, if you didn't feel, look, this room, the chairs that you see there, the room was all changed because of your feedback, yeah? So your feedback is important, yeah? So if you have time, I think it's only 5-10 minutes you can do your view online. You did that, right? In previous years, right? So please try to do because it's very nice to have your feedback, all right? So that we can improve. Okay, so going back to our problem here. So what we are going to do now is, so this is the situation of our airfoil in these conditions that I've told you. What we are going to do is now summation of moments. Summation of moments about the pivot point equal to 0. You might be thinking, why equal to 0? Why is not equal to mass times acceleration? Well, because at this point, we are doing static aeroelasticity. Next week, we are going to do the dynamic, and then, yes, that is going to be equal to mass times acceleration. Yeah. Now, for the case of summation of moments, is second moment of inertia times the angular acceleration, right? Something like that. But for static aeroelasticity, summation of moments equal to 0 is the equilibrium equations. And we want to see what is going to happen to this airfoil, which is going to be something very interesting. I think you are going to enjoy, I hope. All right, so there's some more things I need to tell you. So we are going to consider small angles for this analysis. So this angle of attack, alpha, is going to be a small angle. Right? So we can basically say that sine of alpha approximately equal to alpha, and cosine of alpha, if it appears somewhere, equal to 1. Yeah? Small angles. That is another assumption in this model. We are going also to use linear aerodynamics. Linear aerodynamics. What is this? Well, I think you should know by now, but just in case, you remember the lift coefficient versus the angle of attack. You get curves like this for a cambered airfoil, and then you get the stall and something like that, right? Remember these curves from aerodynamics? So linear aerodynamics, it means we are in this region here, in the linear region of our airfoil. So this slope here, I'm going to say is equal to CL alpha, or if you want, CL alpha is going to be equal to the derivative of CL in order to alpha, which is the slope of that linear part of the curve. Okay, so this is what I mean with linear aerodynamics. And then I can say that my lift, for example, my lift is going to be equal to the dynamic pressure, remember? Which is 1 over 2 density velocity square. Remember this? This is my dynamic pressure. I need to multiply the dynamic pressure with the area, S. And then I will need to have, oops, what is this? Come on. Yeah. And then I will need to have the lift coefficient. This is my lift, but I'm going to, so QS, my lift coefficient I'm going to say is equal to my CL alpha, which is the derivative or the slope times my angle of attack. So this CL times angle of attack is going to be my lift coefficient for a specific angle of attack, right? Okay? So nothing new so far for you. These are the assumptions for this model. So let me copy now this guy and put it in a different page. Great. One more thing I'm going to introduce, which is going to be new, is this angle of attack alpha will have two components, and this is very important for you to understand. One is what we call the rigid component, alpha r, which is basically the angle of attack you have been treating in aerodynamics. You are assuming the wing like a rigid wing, right? No deformation of the wing. But now, in aeroelasticity, our wing will deform. Yeah? So I'm going to say the total angle of attack alpha will have one component which is due to the rigid component, which is due to the angle of attack from aerodynamics, plus an aeroelastic component, theta, which is the variation in the angle of attack due to the wing deformation. Now we are going to have not a rigid wing, but a wing that is deforming. And of course, when it deforms, imagine, for example, the torsion of the wing can introduce this angle theta. That will change the lift. Yeah? So, in my lift equation, I can say that my lift is going to be equal to dynamic pressure times the area times the slope of my lifting curve times my angle of attack alpha, which is going to be alpha r plus theta. Okay? So if you want, this term here is my total angle of attack. Nothing special so far. Another thing we need to consider is the moment at the aerodynamic center, which is given by the dynamic pressure times the area of the wing times the chord times a pitching moment coefficient. Okay? This is the equation that you learned, I think, in aerodynamics for the moment at the aerodynamic center. All right, very good. So if we now do our summation of moments about point P, let's see all the moments we have. So there's going to be a convention here. Nose up means positive moment, which is a bit contrary to what you learn in year 1 in statics, right? Remember I said anti-clockwise moment is positive. Here, nose up, positive, right? Moment. So the first moment we have is the MAC. We can start from anywhere, but let's start with this MAC here. Moment produced by at the aerodynamic center. So that MAC given by this equation is QSC times the pitching moment coefficient. So this is my MAC. As you can see, that moment with that initial orientation I did put in the figure is going to produce a nose up for the aircraft, right? The other moment we can deal now is the moment produced by the lift about point P. That moment produced by the lift is going to be also nose up, so positive, so plus. The moment is equal to the lift, which is the force, which is given by this equation here, which I can write like this, QSCL alpha, alpha r plus theta. So this is the lift. I need to multiply now this by a distance to have a moment. And that distance is this one here. Look at this. Yeah? Which is XP minus XAC. The next term we need to consider is the contribution of the weight, which is at the center of gravity. So that weight is going to be nose down, so negative. So minus, I will continue here below, minus. And the weight is the force, W, and I need to multiply by this distance here from here to here, which is XP minus XCG, right? XP minus XCG. And now we need to consider the moment produced by this torsional stiffness at point P. So when you try to rotate the airfoil nose up, the stiffness will impose a moment trying to bring the airfoil nose down, right? So that moment is going to be nose down. And that moment is equal to, so nose down means negative, first of all, and that moment is going to be equal to the torsional stiffness, which is K, times the torsional angle. And that torsional angle is not alpha r. Alpha r is the aerodynamic angle of attack. So when the airfoil rotates due to torsion, the angle we need to consider is the aeroelastic angle theta, right? So I need to multiply this K by theta. And this will give me the torsional moment. Make sense or not? And if you look at this figure, that's all we have. So this needs to be equal to 0 to be in equilibrium. Again, we are dealing with static aeroelasticity. And I'm going to copy this equation here. To a new slide here. Okay. So what we're going to do now is we're going to solving for theta. I'm going to solve this equation for theta. So if you do that, well, you have theta here and here as well, right? So we need to organize just a manipulation. So if you do that, you get, all right, so you will get on the left hand side QSC CMAC plus QSCL alpha times alpha R times XP minus XAC minus W times XP minus XCG. This is going to be equal. Is going to be equal to what do I have on the left hand side? Well, I have K, and then I have minus QSCL alpha times XP minus XAC, and this multiplies theta. Now it's much easier to get the result for theta, which basically is going to be theta is going to be equal to, I'm going to copy this guy, copy, put it here, and is needs to divide by, first there's a curved bracket that is missing there, so this needs to divide by this K minus, basically needs to divide by this, right? Okay. So this is what happens. So when you apply that lift and that pitching moment on your wing, if you consider the deformation of the wing, it will deform by an angle, which is given by this equation that you have here. Okay, is given by this equation here. And we are going to be looking now. Let me copy this equation to a new slide. Look at this important point now. If the denominator of this equation, if the denominator, this term, is equal to 0, that angle, theta, goes to infinity. And the question is, can this denominator go to 0? Well, if this xp minus xac is positive, yes, it can go to 0. xp minus xac positive means that our pivot point P is AFT of the aerodynamic center, which is usually the case. So if my, for example, if my aerodynamic center is here, that angle theta can never go to infinity, right? So we will not have divergence. But the most common situation is when our aerodynamic center is in front of our pivot point. And in that case, this xp minus xac is positive. And then what we have in the denominator can be equal to 0. And when that happens, or when k minus qscl alpha xp minus xac is equal to 0, is when we get divergence, or is when we get this angle theta going to infinity, which is the end of your aircraft. If I solve now this equation for the dynamic pressure, which is not difficult, you will get torsional stiffness in numerator and SCL alpha xp minus xac. I will call this dynamic pressure as my divergent dynamic pressure. Yeah? And the good thing about this, not the good thing, so the dynamic pressure is 1 over 2 times density times the square of velocity. I can then predict what is the velocity my aircraft can fly, or what is the maximum velocity my aircraft can fly before it gets into a divergence, or before it gets into that critical point where my angle theta becomes infinity and my lift becomes also infinity. And it's the end of your wing, is the end of your aircraft, right? So we will call this velocity the divergence velocity, UD. If you just replace dynamic pressure by this expression, you get your divergent velocity equal to 2k over rho SCL alpha xp minus xac. Yeah? And you can say that this UD is the speed at which divergence occurs. Right? So, So what we usually desire is to have this divergence speed as high as possible, right? So there are different ways of doing that. Increase the torsional stiffness of your wing, for example. Decrease the slope on your lift curve, which might not be good because you lose lift, right? So this might not be a good thing to do. You can play with the density. Well, okay, you can play with density. Not much you can play because when you go flying higher, it means your density becomes smaller. That contributes positively to the divergence velocity. But another thing you can work is this difference between the location of the pivot point and the aerodynamic center. So you can play with the location of the aerodynamic center as well. The smaller this difference, the better for the divergent velocity, right? Okay. A couple more of things before we. I think I'm not going to start the. I think I said here I will deal with. So divergence, yes, we are doing that. But aileron reversal, I think, it's better not to start today because then I will have to hand in the middle of the demonstration. So it's better to continue next week. from the aileron reversal. But there's a couple more of things I would like to say for the static divergence. And in order to say that, we are going to do some more assumptions. Otherwise, this becomes quite complex. The first assumption is we are going to use a symmetric airfoil. It's okay, just to demonstrate what I want to show you. We can use a symmetric airfoil, makes our life easier because the pitching coefficient for the moment for a symmetric airfoil is going to be equal to 0. So it simplifies our equations a little bit more. Another thing I'm going to simplify is I'm going to say the location of my center of gravity is going to be coincident with the location of my pivot point. So if that is the case, what is going to happen then is xp here. If this is the case, what is going to happen is the weight drops off from my equation, from my equilibrium equation for the moments, right? When I do summation of moments about point P, the weight will not appear there. Right? So these are the two assumptions I'm going to make just to make our life easier for what I want to tell you next. And we are going to use this equation. So the equation for the divergence of the dynamic pressure, which I'm just going to copy here. So I'm going to use this equation because I want to get my torsional stiffness, which is going to be given by the divergent dynamic pressure times the area, the slope of lift coefficient times xp minus xac. Okay? And another equation I need to use is this one in the top for the aeroelastic angle theta. So I'm going to put it here, but due to these two assumptions, many things are going to go away. The first one is this one, because the pitching moment CMC equal to 0, so that term disappears. The other one is the weight term, which is this one, also goes away. Yeah? The other thing I can do now is to use this equation for the torsional stiffness and replace here where I have the torsional stiffness. That's what I'm going to do now, right? Let me just copy this. Copy. Let me get rid of the torsional stiffness there and paste. Shrink a little bit. And then I can maybe move all of this a little bit better. Okay? So I'm just doing some mathematical manipulations, nothing special. What else happens here? Look at this equation now. The slope of lift coefficient cancels out. I love this bit. This xp minus xac cancels out as well. Another thing that cancels is the area, S. So at the end, we get this theta equal to something which is Q alpha R in the numerator, and in the denominator we have the divergent dynamic pressure minus the dynamic pressure. Okay? Or if you divide the numerator and the denominator by Q, by dynamic pressure, you get alpha r qd over q minus 1. All right? Okay, and now we are going to consider two things. The lift that is generated by the aerodynamics of the angle of attack alpha r, the rigid angle of attack. So we call that lift the rigid lift. Rigid lift, if you want, is, I can write here, lift generated by alpha r. Is the lift due to the aerodynamics, considering the wing as rigid, yeah? And then we are going also to consider a variation in lift due to this aeroelastic angle theta because of the deformation of the wing. And what I'm going to do next is to see the ratio between the change in lift over the rigid lift. Okay? And for that, I'm going to use this equation we derived, this one here. Okay? So I'm going to copy it here. Just for our reference. So delta variation in lift is going to be the slope of our lift coefficient times our angle theta, changing lift due only to the deformation of the wing, and the lift. Of course, this is okay. I can be more accurate. In fact, is not only this, right? There is something more, which is the dynamic pressure times the area of the wing, right? This is more accurate. The lift generated when we consider the wing rigid is also given by dynamic pressure times the area of the wing times CL alpha, but now times alpha r, the angle of attack only if we consider the wing rigid. So this, all of this cancel out, and then we have at the end theta over alpha r. Theta over alpha r will give me the variation of lift over the lift when we consider our wing rigid, right? So if I replace now theta by this equation here, not lift, sorry, my angle theta by this equation, I will get alpha r over alpha r times qd over q minus 1. This alpha r cancels, yeah? And then I can say this is going to be equal to 1 over qd over q minus 1. And for convenience, I'm going to continue here. I'm going to write this last expression. So what I'm going to do is I'm going to multiply both the numerator and denominator by the dynamic pressure. So I will get in the numerator 1 times dynamic pressure, and here I will have qd minus q. Yeah? Make sense? Nothing special. Now what I'm going to do is I'm going to divide again the numerator and denominator by the divergent dynamic pressure, Q over QD.
and here I have 1 minus Q over QD. And then I can so what you can see from this equation again, if you look at the denominator, if my dynamic pressure is equal to the divergent dynamic pressure, I get 0 in the denominator, and then my angle theta goes to infinity, right? So we get a curve something like this. If I have here in the horizontal axis the dynamic pressure over the divergent dynamic pressure, so this goes, of course, from 0 to 1. 1 is the maximum. If I have here the variation in lift over the rigid lift, we will have a curve something like this. It goes to infinity when it approaches 1, which means we will have a huge amount of lift. Okay? Now, just to finish, another important thing, which is very convenient for the wind tunnel experiments, if you want to go to wind tunnel, and continuing from this equation, we can do some manipulation of this equation as well. So I'm going to invert the left-hand side, so I'll get alpha r over theta, so I need to do the same for the right-hand side. Okay? And now I'm going to send alpha r, this alpha r, from the left-hand side to the right-hand side. And then you get, if you do that, you get 1 over theta is going to be equal to QD minus Q over alpha RQ. Nothing special, I'm doing nothing special. If I continue, I can say I will have QD over alpha R times 1 over Q minus 1 over QD. Which is an equation that you are familiar with. Look, if you consider the left-hand side your y, you are going to have a slope m times 1 over q minus b. If you say this 1 over q is your x, this is the equation of a line, isn't it? Yeah? So I can say if I try to plot, and now this is the important bit, if I try to plot if I have here, sorry, let me just 1 over q in the horizontal axis, 1 over q, and in the vertical axis 1 over theta, I will have the equation of a line, which is this one. Okay? So look at this. When in the vertical axis I have 0, when I have 1 over theta equal to 0, this means theta tends to infinity, right? 1 over infinity is equal to 0. Theta infinity is my divergence. Yeah? So this distance from here to here, this point from here to here, is my 1 over qd. So if I can get this line, the intersection of this line with my horizontal axis, that distance from 0 is 1 over qd. So I can calculate my divergent dynamic pressure. But why do I need to have this plot? The reason is, if you are in the wind tunnel, yeah, if you are working with a small speed in the wind tunnel, you might get 1 point, data point 1, which if you want is equal to 1 over Q1. So you can measure the dynamic pressure Q1. And if you get a second point, data point 2, 1 over Q2, if you increase a bit more the speed in your wind tunnel, you can get a second point. So once you get 2 points, you can draw a line, isn't it? And then you can predict, once you draw that line, you find the intersection of that line with the horizontal axis. And then you get, immediately from the wind tunnel, you get your divergent dynamic pressure. And of course, your divergent speed. Only from 2 measurements in the wind tunnel. That's what this equation is telling us. Yeah? And that's why I'm doing this. So you can see, I show you how you can get analytically the divergence velocity. And I'm showing you now how you can, in the wind tunnel, get your divergent velocity as well. Just one more thing. This distance here, from here to here, is going to be 1 over half r. Okay? Because this is when your, if you look at this equation, this is when your 1 over q is equal to 0. So when 1 over q is equal to 0, this term becomes 0. So you will get QD will cancel with QD. You'll get 1 over theta is going to be equal to 1 over alpha r, right? Anyway. All right. Any questions? Static divergence. So it's very important thing in the design of your wing, right? We should not allow the wing to reach that point. So we need to try to design our wing so that the divergent velocity is as high as possible. It means you can fly faster without the divergence occurring. Of course, if you look at this plot, the closer, so imagine this point here, let's say 0.6. It means your Q over QD is equal to 0.6. Or if you want, your dynamic pressure is equal to 0.6 your divergent dynamic pressure. So you are getting closer. So it means you will get, due to aeroelastic effects, you will get more lift in your wing because of the deformation of the wing. So the closer you are to your divergent velocity when you're flying, more and more lift you will get. And that can be very dangerous. Yeah. So the ideal is to be flying as far away as possible from your divergent speed. Okay? All right, so next week we'll start from aileron reversal, which basically, in a nutshell, very quickly, when we deploy a flap, we always think we are getting more lift. Not always the case. Yeah? When we have the wing deforming again, it's going to be a point when, if you deploy more the flap, you will get, in fact, less lift. So that point is what we call, that transition point is our aileron reversal. We are going to start from there next week, all right? See you guys.